Okay, welcome all of you. See, in the last class, we started discussing about a new experiment called resolved type experiment, which is completely different from other experiments we discussed, where we were correlating the information between two abundant spins or between abundant spin and the rare spin, and also between two dilute spins by using a 2D inadequate experiment. They were all correlated type experiments. But there is another type of experiment where NMR parameters can be separated out. We have most important two parameters in NMR called J couplings and chemical shifts. They will be invariably present simultaneously in the one dimensional spectrum. That will complicate the analysis due to enormous complexity because of n number of interactions for each of the protons or each of the nuclei depending upon the interaction strength. Multiplicity pattern will be enormous. So, analysis will be very difficult. One way out is to separate the interactions in two different dimensions. That is what is called J-resolved experiment. We can resolve the two parameters in two dimensions, and this is what I discussed about J-resolved. J-resolved is nothing but a homonuclear sequence like a spin echo. It is a 90 tau 180 tau sequence, and what is going to happen because of the 180 pulse in between in the homonuclear case, chemical shifts are refocused, but J couplings are not refocused, they continue to evolve, that we discussed very long back. So, instead of fixing the T1, vary the T1, and I told you the intensity of the when I take the example of a doublet, two coupled spins, the intensity of the two peaks keep varying, gets modulated as a function of T1, and also it depends upon the strength of interaction. We saw that, and I took another example of CH2 group AX2 coupled spin system, where we monitor the triplet. In the case of the triplet, I said central peak do not precess. This is what we observed also when we discussed spin echo. Only outer components of the triplet start precessing in the opposite direction. Their intensity also gets modulated as a function of T1. The intensity change vary as a function of T1 and also interaction strength. And finally, we observed that when we do the two dimensional Fourier transformation of this, in the F1 dimension, we are going to get the peaks whose separation gives you J coupling. In the direct dimension, you have both the interaction parameters present, like chemical shift and J couplings, both are present. And that is why we saw that when we took the example of a triplet and a doublet, we saw peaks were tilted like this. When we saw these peaks, they were tilted like this. I see, I am sorry, here they were tilted like this. This is a triplet, and of course, in the triplet, because in this dimension both chemical shift and J coupling are present, you will see that one peak is moved to the left, other is moved to the right here from the center of the chemical shift. That is what happens in the 1D spectrum. From the center of the chemical shift, one of the coupled peak is moving to the right by half J, other is to the right. Of course, in the case of triplet it is J, this also J. In this case of this one also, from the center of this peak start moving on either side. This is here, this is the peak quartet, it is going to be a quartet. They behave similar to CH peak like a doublet, but both the cases, in the CH case the center is a chemical shift, here also central peak is a chemical shift, but in the indirect dimension what we can do is we can measure J coupling here between this and this, between this and this, this and this, this and this, that gives you J coupling. Very easily you can get J coupling information. But another thing what we can do is, look here, everything appears tilted by 45 degree. There is a 45 degree tilt here. Why can't I tilt this thing by spectrum by doing what is called processing? I can do a different type of processing. Tilt the entire spectrum by 45 degree. Then the peaks which were here started moving this thing, peaks which were here started coming like this. For example, in this case, when I tilt it, what is going to happen is the frequencies will not change. Only this moves here, this moves here, and this will move this side, this will move this side. Exactly here this moves this side, this moves this side. This is the center. This is what is called a 45 degree tilt. If you do that, you get a triplet here, you get a quartet here. From the center of the triplet you measure, you get J coupling, and here J coupling is obtained from adjacent separations. Measure the adjacent peak separations, you are going to get the J coupling. This is called 45-degree tilted J-resolved, not projection, the 45-degree tilting of A3X2 or A2X3 spin system. A2 is going to be a quartet because of X3, X3 is going to be a triplet because of this, and that is what we see, triplet and a quartet. This is a simple J-resolved experiment. We resolve the chemical shift J coupling in one dimension and chemical shift and coupling in the other dimension. And by doing the tilting, the advantage is we remove J coupling in this dimension also. Alright. How it is very useful, especially in understanding the complex spectrum. You can just say an example like this, an hypothetical molecule. I am going to put different colors here, a complicated 1D spectrum. This is how it is. That means I have put deliberately color. I know this is a doublet, I know this and this is a triplet, this and this doublet, this and this is a triplet and doublet and triplet, and deliberately it is numbered, colored, and you can see that there are overlaps here. There is a complexity, spectral complexity is too much to extract the coupling information. This is where J-resolved comes into the picture. What we do is we take the J-resolved and tilt it by 45-degree. If you do not tilt it by 45-degree, you can still get peaks like this. It can still be okay, but then we are tilting it by 45-degree. Advantage is you can see that these two peaks which were a doublet is here. This and this peak which were doublets here. The triplet comes here. Doublet, triplet and doublet. Such a complex spectrum here. What we did? We simplified it by just removing one of the parameters, resolving it, taking it away, putting in different dimensions. Our analysis becomes simpler. Directly you get chemical shifts here and measure here you get J couplings. This is the biggest advantage of a J-resolved experiment, where the spectral analysis gets drastically simplified. Okay. Another biggest advantage is the projection of the 2D spectrum on the F2 axis and the direct detection axis gives rise to what is called a broadband proton decoupled proton spectrum. Remember we discussed broadband proton decoupled carbon 13 spectrum. What did I say at that time? We can irradiate at the radio with a second radio frequency radio frequency at the proton chemical shift, center of the proton spectral width with a certain power larger than the coupling strength. Then we can break all the carbons coupled to all the protons broadband in a single experiment. That is what we discussed. That is easy. That type of heteronuclear broadband decoupling is very easy to do, because the spectrometer frequency is different, observation detection frequency is carbon 13 and irradiation frequency for decoupling is proton frequency. They are several megahertz apart, easy to do. Whereas if you want to do the broadband decoupling of the proton while detecting proton, it is not easy, it is very challenging, because when you are decoupling, you are already signaling, you have brought this magnetization XY plane, you will completely disturb it when you apply RF pulse for decoupling. It is not easy, it is very challenging. So, but if we can decouple somehow, it is possible for us to get the coupling information in one dimension and chemical shift in the other dimension in a very simple manner. That is possible, but the simplest experiment you can think of for such broadband proton decoupled proton spectrum is taking the projection of the J-resolved spectrum on the F2 axis. This is what it is. We take the projection. Earlier there we saw doublet, triplet, everything was there. It was a complex spectrum. Now what we did? We took the projection. See, look at it, this gives you chemical shift, this gives chemical shift of this proton, and this gives you J coupling. What did you do here? No HH coupling. JHH is completely removed. because you are removing all proton-proton couplings here, it is broadband decoupled. So, directly you can get the chemical shifts. This is the beauty of this experiment. 2D J-Resolved, if you take it and take the projection of it onto F2 axis, you are going to get chemical shift of all the protons. Fantastic broadband decoupled proton spectrum. This is an example, a 45-degree tilted pulse. Beauty what you can see here is a pentate. This pentate comes because of two peaks which are overlapped, but they are two different chemical shifts. Look at it, 1 3 3 1 1 quartet, 1 3 3 1 1 quartet, but each of them has different chemical shifts here that you can extract easily. Two quartets, 1 3 3 1 1 3 3 1 quartet, and this is chemical shift of one of the quartets here, and the chemical shift of other quartet is here, and this quartet 1 3 3 1 triplet, doublet and a singlet, everything is there in a hypothetical spectrum where you know how to resolve it. So, generally what is going to happen is the homonuclear couplings are between 1 to 20 hertz, not more. We are always HH coupling, if you are looking at it, very rarely you get more than 15 or 20, all within that. So, what the type of experiment what you have to do in the T1 dimension, and the experimental aspects I never discussed because it was in the previous courses. I extensively discussed about parameters for setting the parameter for experiments. But anyway, T1 number of points we require to get the better resolution, in the especially in the 2D J-Resolved. If you take 256 points and 512, the spectral width has to be very small, only to cover 20 hertz or 50 hertz, maximum 20 or 30 hertz you put it, or 50 hertz. The 512 points, the hertz per point becomes very small, you can calculate. If for 50 hertz spectral width to be covered in the with 512 point, if you have to digitize, your digital resolution becomes 0.09 hertz per point. That means you can measure the J coupling with very high accuracy in the J-Resolved, because we do not have to cover a large spectral width. And this is a simple example, ethyl crotonate, and you see here lot of things are crowded here. Of course, looking at the spectrum one can easily assign it, but if you want to do the 2D J-Resolved, you can extract it very easily like this. This is a triplet, this is a doublet coming because of various reasons, and it is in fact doublet of doublet. You see doublet of doublets are here. This is a quartet, two quartets are here separated out, and easily you can interpret the spectrum. And in a very complex molecule, this is where the beauty comes into the picture. Look at this spectrum of this molecule, very complex molecule. Look at proton spectrum, very complex. You have both J coupling and chemical shifts present here. It is not possible to analyze so easily. Look at this crowded region. See, you have to identify which are the coupled multiplets. If you take two coupled spins, which is triplet, which is the quartet, which are the quartet peaks, which are the triplet peaks, when they are overlapped, identification is a challenge. But now, by doing this 2D J-Resolved, we can assign all the peaks. You see, they are all resolved here. This is J-Resolved, J dimension, this is the chemical shift dimension. Especially when you take the projection of it, you get chemical shifts easily. This is the 45-degree projected J-Resolved spectrum of this complex molecule. You get chemical shifts here, and in this dimension you measure J couplings. You see how beautifully the complexity of the spectrum could be reduced, and analysis becomes fairly simple. This is the measure. And one more advantage is, I want to tell, consider a molecule like this. We have phosphorus, proton, we have proton-proton couplings here, and phosphorus is also abundant spin that can also couple to proton. If I take a proton spectrum, we have proton-proton couplings and also proton-phosphorus coupling, both are present. So, that means in this is a proton spectrum, you have both homonuclear and heteronuclear couplings are present. What are homonuclear couplings? JHH plus JHP is heteronuclear, both are present. But what we can do is, we can extract only heteronuclear couplings. How is it possible? We have to remove homonuclear couplings. How do you do that? Just now we did, do the proton-proton J-resolved experiment and take a projection. Then in this dimension you get only chemical shifts, and this then you have removed the HH coupling, you are getting only proton chemical shifts, and you are going to get proton proton couplings here, and here you are going to get HP couplings. See, for example, multiplicity pattern is here, center of this correspond to chemical sheet of this, and this is this multiplicity pattern correspond to phosphorus proton couplings here also. So, very easily you can measure the heteronuclear couplings by doing homonuclear J-resolved and taking a projection of 45 degree, tilted by 45 degree, and take the projection. This is what you are going to do, and this is a simple example of a molecule. It's a molecule here 2,3 difluoropyridine. There are 3 protons here, 3 groups of protons are here, and each proton is coupled to 2 fluorines. You get HI coupling and HF couplings. This proton can couple to this and also these 2 fluorine. Of course, FF coupling you do not see, that is a passive, there are passive spins, you do not see it. So, if you look at the proton spectrum, there are 3 different protons, each of them is a multiplet because of both homo and heteronuclear couplings present. But how do you extract only HF couplings from this molecule? What we do is, we do the proton experiment J-resolved and take a projection here. When you take this proton and take a projection here, this projection gives me only HF couplings here. Here this separation gives me HF coupling, because proton coupling is removed. Whatever the multiplicity you are getting here as a projection, on this projection whatever you are getting are fluorine phosphorus coupling. To confirm that, if you do the fluorine decoupling, same 4 peaks you are going to get here. This is what it is. So, we can get the heteronuclear couplings from the homonuclear J-resolved spectrum, and then taking a tilted by 45 degree and take the projection. That helps in getting the heteronuclear couplings. So, these are all homonuclear J-resolved experiments and lot of advantages we discussed. Can we get a heteronuclear J-resolved also? Everything is possible in NMR. Not anything is not difficult at all. Why not we get the heteronuclear J-resolved spectrum? What we have to do? This is a very easy pulse sequence, we know that. When you have proton and X nuclei, we discussed this also during spin echo modulation and spin echoes. When we apply both these things at the 180 pulse simultaneously, and both J will evolve. That we know that we all discussed a lot about it. And of course, this is a sequence which we did for homonuclear J-resolved. Simultaneously here we are also doing decoupling here. When you are decoupling X nuclei, you are doing decoupling. What is the advantage? You break the coupling between carbon and proton, get individual resonances, plus there is an NOE enhancement that will also come into the picture. This is a sequence. Simultaneous 180 pulse on 1H refocuses both the carbon 13 chemical sheet, but the heteronuclear J coupling will continue to evolve. That is what I said. In the heteronuclear J-resolved, in the spin echo when we discussed, we said simultaneous application of 180 pulses on both the channels, both X nuclei and proton, or both the heteronuclear spin, will make sure coupling will evolve, but chemical shifts get refocused. With that idea, that is simple pulse sequence design, we can continue to do the experiment, and in the T2 dimension collect the spectrum of heteronucleus like carbon and nitrogen 50 and do the decoupling of protons. So, this is what happens. So, what is going to happen? During the spin echo sequence in the T1, chemical shifts are refocused, signal get modulated only due to heteronuclear J coupling. It's exactly similar to homonuclear J coupling what we discussed. The splitting pattern, if the components of the multiplicity, there are several components of the multiplicity, their intensity keeps changing depending upon the delay T1 and the interaction strength. That continues to happen here also. Okay? And there is an experiment for doing this. This experiment is called spin flip or proton flip method. We can do that. Okay, we will understand those things later. This experiment is what is called a proton flip experiment or spin flip experiment. Heteronuclear J-Resolved spectrum tilted by 45 degrees like this. This also get J coupling and chemical shift on the F2 dimension. So when you are tilting it, see for example this is CH2 carbon. CH2 is a triplet because of coupling with carbon with 2 protons. CH3 is going to be a quartet. Beautiful. Again CH3 quartet, quartet, triplet, triplet, and this is CH is a doublet. Very easily you will measure for this molecule all the carbon proton 1 bond couplings easily. Simply do the experiment, tilt by 45 degree, you will measure the J coupling and projection gives you corresponding chemical shifts. Okay. What happens if there is no 180 pulse and only proton decoupling, especially in the proton channel here? If there is no 180 pulse, simply you should understand by now, since we have discussed J modulation at stretch, if there is no 180 pulse, it means what is going to happen? 180 pulse and X force refocus chemical shifts and also heteronuclear J coupling, because when we discuss J modulation I said 180 pulse and one of the heteronuclear will refocus J couplings and also that particular chemical shift. If the 180 pulse is applied on proton, it refocuses the heteronuclear J coupling and but refocuses proton chemical shifts, not carbon. So, but simultaneous application of 180 pulses on both refocuses the chemical shifts but not the J coupling. In which case, if you apply only single 180 pulse and not on proton, then it is not a useful experiment, it is a useless experiment. That does not give you any information. So, you must apply 180 pulse simultaneously on both proton and carbon channels. So, heteronuclear J-Resolved can be done by what is called a gated decoupling method. This is what is called a gated decoupling method. What we do here is, in the previous thing, if you see carefully, if you see here, we started decoupling at the time of acquiring the signal. See here, we start collecting the signal here in the T2 dimension and we apply decoupling power simultaneously. And NOE is done here and NOE is done here. Whereas here an experiment is done where decoupling starts even before during the first half of the T1 period. This is what is called a gated decoupled experiment, where X-spin chemical shifts are refocused due to 180 pulse in the middle of the T1. But heteronuclear J coupling continue to evolve for this period, but not this period. That means heteronuclear coupling will evolve for half a period, then afterwards decoupling will break it. You will decouple both of them, there is no coupling. So, it evolves only for half a period. What does it mean? The J couplings are reduced by half. It is an experiment, you get enhanced intensity, but J couplings are reduced by half. This is what is going to happen. Look at this heteronuclear J-Resolved experiment on this menthol molecule. Different carbons are identified here. For example, carbon 9, somewhere here CH3, it is a quartet. But do not directly measure this and say this is J coupling. It is only half J, because it is a gated decoupled heteronuclear J-Resolved. I am just giving an example how we can do different types of J-Resolved experiments. To enhance the intensity we can do this, but only thing is you have to be careful in interpreting so the J couplings are not just full value, it is half the value. And measuring of the long range J couplings we can also do. So, we got only 1 bond J couplings here in all these experiments. Triplet correspond to this quartet correspond to CH3 coupling, and this is CH and this is CH2 is a triplet like that. But then what about long range coupling? That also we discussed when we discussed about carbon 13. For example, this carbon can couple to or this carbon can couple to this proton. 2 bond coupling may be present. Can we get the J coupling? Long range coupling. It is possible to do it. If you want to measure the long range coupling, certain things have to be done. First, we have to remove 1 bond coupling because that will interfere. similar to your HSQC, HMBC. When you are doing HMBC, you are removing one bond coupling, one bond correlation. Exactly here, one bond JCH has to be, we have to remove the evolution of that. That is one of the requirement. Secondly, the digital, of course, the advantage of this, when you have the long range coupling, spectral width is very small. The digital resolution becomes better. Digital resolution gets enhanced. So, as a consequence, long range coupling of the order of 10 to 15 hertz, you can measure precisely with a very high accuracy, you can measure. But only thing is, we have to design an experiment for that, and this is an experiment for that. What it does? Of course, this you know is a homonuclear spin-Yakob sequence, but on the proton channel we are applying a bird sequence. Yesterday or day before yesterday I discussed about bird sequence. Bird is a 90, 180, 90 here sequence like this. What this sequence will do? This sequence, when you apply, I discuss this and also explain with a vector diagram. Selectively it inverts carbons attached to proton 12, proton attached to carbon 12, they get selectively inverted. This bird has no effect for carbon 13 attached to protons. Only carbons 12 attached to protons are selectively inverted. That we saw that, especially when we were discussing HMBC, I explained this thing. All right. So, this is what is written here. It inverts those protons that share long range couplings. This experiment. Protons directly bonded remain unaffected here in this sequence, not in the bulb, I am telling. In the sequence of the J-Resolved experiment for long range, this is what happens. It inverts only those protons that share long range couplings. Protons directly bonded remain unaffected. At the end of T1 period, 1JCH is refocused, only long range couplings are retained. We design the experiment in such that long range couplings, one bond couplings are refocused and only long range couplings are retained. And the F1 dimension gives only long range couplings here. That is the advantage. And this is a selective heteronuclear J-Resolved experiment. You can do it selective and non-selective both. In this sense, in the previous experiment, here you can do it for all the peaks to get the long range couplings. You suppress one bond J coupling and all other long range couplings will be observed. But same thing, I can ask a question. There are so many protons, so many carbon. Can I get the long range coupling only for a particular carbon? That is, I have a carbon here and then there are long range couplings for the here. Can I get only these couplings for only for one particular carbon? It is possible. The same experiment we can make it selective. This is called selective heteronuclear J-Resolved experiment, in which case we apply a selective pulse, not 180 pulse. 180 pulse is selectively, not a broadband hard pulse, it is a selective pulse on a particular carbon, I am sorry, particular proton here. We are applying that. When you apply that, then what is going to happen is selective pulse invert the selected proton only. All the JCHs are refocused except for that selected proton. All the JCHs are refocused, only for that selected proton carbon couplings are retained, long range couplings are retained. So, indirect dimension always displays simple doublet, triplet, quartets, etc. because one carbon experiences coupling with remote protons, long range coupling. It can be one proton or two protons or three protons. It could be maximum doublet or a triplet or single quartet like this. This is what happens. This is a selective long range heteronuclear J-Resolved experiment of one molecule like this. And this is the molecule which is selectively irradiated. And there are 4 different carbons here, 1, 2, 3 and 4. This proton can experience different couplings. What are they? It can experience, I am sorry, it can experience coupling between, let us say 1, 2, 3 bond coupling to 1 here 2.8 hertz. This measured separation gives you 2.8 and 2 if you consider here this proton 1, 2 bond coupling to this proton. For 4, you can consider here 4 is here 1, 2, 3 and 4 bond. 4 bond coupling very small, 1 hertz. See measured values. See in the long range coupling selectively for a particular proton, selectively invert. Only for that proton the couplings are retained, for all others are refocused, and we can measure long range couplings very precisely. And we can use this to distinguish various things like endoform, exoform, etc. That's very, in fact in this molecule it was used to define endo and exoform, because the endo and exoforms of this molecule, the coupling strengths are known for us. The selective long range heteronuclear coupling can also be done with a proton detection. But remember here in this experiment what we did? Here we are detecting carbon, decoupling proton. Always I told you decoupling of detection of a heteronuclear like abundant dilute spins like carbon 13 is very time consuming. That is the advantage of doing HSQC. What we did, we detected proton by transfer the magnetization from carbon to proton and back transfer. Why can't we do that? If you do that, we can detect the same the J coupling experiment can be designed with proton detection. Then your experiment becomes faster, sensitivity will go up. All we have to do is the same. With this you are very already familiar with this. It is an inept sequence. This is your selective J sequence, heteronuclear J sequence with a selective pulse on the proton, reverse inept to collect the signal back to proton and detect. Exactly what you did for the previous pulse sequence with a selective proton, you selectively invert and get the couplings to different carbons for a particular carbon. Then what we are going to do is we can get the couplings to remote long range couplings, but they are time consuming because we detect carbon 13. Same experiment is done by selective 180 pulse with a polarization transfer and reverse transfer, and this is the advantage. The inept sequence results in polarization transfer. Selective pulse inverts only selected proton. All the JCHs refocus except for the selected proton. So magnetization transfer is back transferred to inept and detected. See, like in this case, if you see here, selected this proton coupling to all the carbons. We are inverting this proton coupling to remote carbons we see. If you invert other proton, that proton coupling to other carbons you see. This is what it is called selective experiment we do. And this is the example of a spectrum of a selective long range heteronuclear J-resolved with proton detection. This is what it is done, selectively inverted this one. H prime is selectively inverted. Coupling of H prime to different carbons you can see here, because we are detecting proton indirectly. Okay. So this is what it is, and this is, with this I told you a lot of things about J-resolved experiment, homonuclear J-resolved, long range detection, long range pulse J-resolved measurement, homonuclear J coupling measurement, and broadband homonuclear decoupled broadband spectrum by getting the projection of the proton spectrum after 45-degree tilt. In the heteronuclear case, we also wanted to enhance the sensitivity by selectively inverting a proton and getting the long range couplings of that proton to different carbons. That can be done with the proton detection by doing polarization transfer technique and then back transfer to proton like inept and reverse inept experiment. Number of things have been done. But remember, what I have given is a tip of an iceberg. In principle, this J-resolved experiments has been modified enormously. There are a number of experiments are available, each of them with an improved version to get a particular information. We have 2-dimensional version, HSQC, it can be coupled with HSQC. It can be coupled with the HMBC also. If you do long range HMBC, if you get a well resolved spectrum, HMBC I said we do always do in a coupled mode. We don't decouple. We can get J coupling also, heteronuclear J coupling. So we can do we coupled with HMBC, coupled with TOXI, and varieties HSQ-MBC, varieties of experiment. If you go, there are number of papers published, lots and lots of papers have been published, lots of reviews are there. Only in a measurement of J couplings, hetero and homonuclear. That many number of pulse sequences have been designed. Many of them have been with improved version and a lot of information can be, excellent experiments have been designed. So I gave you only the principles and fundamentals for sequences, but the idea is similar. The rest of the things are only slightly improved versions to get better information or to get a better resolution, enhance the sensitivity or speed up the data like that. That is the way pulse sequences have been designed. Apart from that, it is all remaining same. So with this I am coming to the end of this J-Resolved experiment. Today we discussed a lot about J-Resolved, and hopefully you understood why it is done to simplify the spectrum, where the information from 2 parameters can be separated out in 2 dimensions to aid the simplified analysis. You may ask me a question, what do I do by getting J-coupling? J-coupling can be utilized a lot for getting structural information. We discussed a lot about Laplace equation. So these are all advantages. This is one such 2D experiment. So with this, the result type experiment I am going to stop. From tomorrow we will start some altogether different type of experiment. Again, it is a correlation experiment, but not through bond, but something else. So we wait for it tomorrow. We will discuss something more. Thank you very much.